Okay, so the purpose of this video is going to be to use the study plan that we published to review for your, not test 3 online, but up here the final exam. The final exam is going to be online. It's cumulative, so you'll get a chance through the study plan to see what concepts will be on it. It's optional, so if you're not taking it, you won't need to watch this video. The other reason I wanted to make the video, since it's optional, I might just publish this in the week that we would be taking the final, so that rather than having a lecture time, you have time just to work on your final and to review. And also because it's optional, I don't know that everybody will need to attend the lecture. So I'm going to just go right in sequential order. I'm going to move right through, and what I'm going to try to do is hit on the quiz me portions. Looks like I might have already done one, so I might have to jump to, unless I can possibly reset that. I'll figure that out as I go through. All right, so I'm going to hit the quiz me button here for the first one. The reason I like to do the quiz me's is because you'll be able to do the practices and kind of get feedback with the quiz me. You kind of do the quiz and then it scores you and kicks it back to you. So I want to walk you through all of these. So all the way back to Chapter 1, determine if the statement is true or false. It is impossible for the Census Bureau to obtain all the census data about a population of the United States. The statement is true, right? This is why we use sample statistics, okay? So I'm going to click through that. Why is a sample used more often than the population? Really, this relates back to the first question, right? It's not that they're more accurate, but it's usually impossible to count the entire population, right? So samples come in very, very handy there. The last one here, all samples are representative, is not necessarily true, right? Simple random samples, or if we use some random element to get a representative sample, that would be helpful. A statistic is a measure that describes a population characteristic. That's false. It's meant to estimate a population characteristic, but it's a statistic describes something from a sample. So if you remember way back to like our first class, keep the two S words together. Sample statistics, keep the two P words together, population parameters. Okay. What are the two main branches of statistics? Okay. We have descriptive statistics and inferential statistics, right? Descriptive statistics will be what you might read in the newspaper. Inferential is the part of purpose of this course where we take probability and make decisions based on what we know from samples and how numbers behave. A sample statistic will not change from sample to sample. That is false. It can change from sample to sample. In fact, it's very likely to change from sample to sample. And we'll go ahead and submit the quiz and see how we did. Okay, so we got all of those right. We can review the test, or we can just move back to the study plan, which is what I'm going to do next. Okay, so Chapter 1, try to keep that very, very basic. Let me get back to final exam online. And now we move to Chapter 2. Trying to major on the majors here. So Chapter 2, I only gave you one question, or at least one flew up in our study plan. So the first thing I do, before I even read this, I want to make some observations that this histogram here is definitely skewed to the left, right? We have a few small values, but the center is over here somewhere around 12 roughly. But then remember, these really low values are going to skew a measurement like the mean. When I add these low values to the total, they make the total lower, and we divide, whereas the median will tend to just kind of hang in the middle. So when we have a tail to the left, it's skewed to the left. When there's a tail to the right, it's skewed to the right. It's important that you remember that distinction. How is the mode determined, right? The mode is the number that occurs most often, so it's the entry that has the highest frequency. Okay. The mode here, the highest frequency would be C, right? That's the highest peak in the graph. Now, because it's skewed to the left, we could expect the mean to be a little bit smaller than the median. So how is the mean, in this distribution, how is the mean determined? The mean is definitely to the left of the median and the mode. This would go mode, median, and mean. The mean is going to be pulled down by those small values that are making it skewed to the left. Where is the mean labeled? He is labeled A. The mode, or the median, is to the, read this carefully. Right of the mean, yep, and to the left of the mode. Yeah, he's right in between there, so he would be labeled B. And we can submit. So, nailed it. Let's keep going. Looks like I have to keep toggling back to final exam review. Measures of position. This would be like percentile z-scores and so on. We've got 5 questions in here. Okay. Determine whether the statement is true or false. The 50th percentile is equivalent to Q1. No, that's not going to be true. It would be equivalent to Q2 or to the median. So usually we call that the median, but Q2 is fine. It's the second quartile. Q1 is the 25th percentile. Okay. Any outlier is any number above Q3 or below Q1. That's not true, right? We had this 1.5 IQR rule where we calculate this length, Q3 minus Q1. We multiply that by 1.5, and we add that to Q3, and we subtract it from Q1, and that is where our outliers would live. So this one correctly describes it, right? It's above the Q3, right? These are going to be high numbers, and then below where we would subtract. That one sort of correctly describes where that would live. Okay. The goals scored per game by a soccer team represent the first quartile for all teams in the league. What can you conclude about the team's goals scored per game? So that they scored fewer per game than 25%. That's not true. I look at the 25% as first quartile. It's how many they scored. So if they're at the 25th percentile, that means they scored they scored higher than 25% of the league, which means they scored lower than 75%. That was a little tricky the way they framed that one. Explain how the interquartile range of a data set can be used to identify outliers. Okay, so the IQR of the data set, we're going to find values that are greater than Q3 plus 1.5 IQR. This is what we just did, right? So if a value is above, I multiply IQR by 1.5 and add it to Q3, or less than, let's take Q1 and subtract the 1.5 IQR from that. Those would be where my outliers are going to live. Okay, and the last one, 9th decile. Okay, so a decile is every 10%. So the 9th decile would be the 90th percentile. It's an easier way of saying it. So its fuel is greater than 90%. Fuel efficiency is greater than 90% of vehicles in its class. Let's see how we did. Okay. Move along again. Let's make sure that we're still on final exam. We'll do a quiz me. So side-by-side box and whisker plots can be used to compare 2 or more different data sets. Each box and whisker plot is drawn on the same number line to compare the data sets more easily. The lengths of songs played at 2 different concerts are shown. Complete parts A through D. So let's take a look at the box and whisker plots, right? We can slide this over here. Concert 1 and Concert 2. So before I do anything, I can see the lengths of the songs at Concert 2 generally tend to be longer than the lengths of the songs at Concert 1. Right? They have a higher median, higher center, but the lengths of the songs at Concert 1 seem to have less variability. Right? They're a little bit more consistent. They're not as much variability in their lengths. So the distribution of Concert 1 is definitely symmetric. Okay. Concert 2, we could say, is a little bit skewed to the right. It kind of has a long tail to the right, so we'll see if skewed right is okay for that one. Which concert has less variation in song lengths? Definitely Concert 1. Okay. Which distribution is more likely to have outliers? Well, the one that's skewed to the right is one that is going to be more likely to have some outliers. If we draw a modified box plot, we would know if there are going to be outliers. So I would say Concert 2 is more likely to have outliers because it has more variation. I mean, more variability, more variation. Let's see if I can move this box so I can actually read this question. I'm just going to close it. Okay. Which concert do you think has a standard deviation of 13.4? Well, let's take a look and see. So standard deviation of 13.4, we want to kind of determine if that's pretty high or pretty low, relatively speaking. So if 13.4 is a higher standard deviation, then that would go with Concert 2. So let's see, Concert 2, because the interquartile range is greater than twice 13.4, for each distribution, at least 75% of the data lies within 2 standard deviations of the mean. 50% of the data lie between Q1 and Q3. Therefore, the difference between Q1 and Q3 should be smaller than twice 13.4. So concert 1, because the interquartile range of concert 2 is greater than 13.4 for each distribution, at least 75% of the data lies within 2 standard deviations of the mean. 50% of the data lies between Q1 and Q3. Therefore, the difference between Q1 and Q3 should be smaller than 13.4. Okay, so this one's a little bit tricky to understand, but they're using Chebyshev's rule here, right? At least 75%, right? So if I'm at the mean and I go 13.4 to 13.1 above and below the mean, then I should have at least 75%. What we're saying here is that here I definitely have at least 75%, right? The IQR here is 224 to 204. That's only 20. So twice 13.4 would be 26.4. So I'm definitely going to have at least 75% here. I won't have at least 75% here. Okay, so we're going to say concert 1 would be the one with the 13.4 standard deviation. Can you determine which concert lasted longer? Probably concert 2, right? Not because it has, let me see. Well, that's a good point. Let's look at this again. Yeah, all we don't know how many songs they played, so that's a good point. The songs tended to be longer at concert 2, but if we don't know how many songs they played, then we really don't know how long the concert lasted, right? Okay, use the box and whisker plot to determine if the shape of the distribution represented is symmetric, skewed left or skewed right. That is symmetric, nice and balanced. No outliers, nothing pulling in one direction or the other. Okay. So the data show the number of hours spent studying per day by a sample of 28 students. Use the box and whisker plot below to answer parts A through C. About 75% of the students studied no more than how many hours? Where's the box and whisker plot here? There we go. Okay, so about 75% of the students studied no more than, so 75% studied no more than 6, right? So you have 25% that studied, this is the Q3, so 75% studied no more than 6. What percent of the students studied more than 3.5 hours per day? Where's 3.5? Right about here. So I'm going to say, oops, 3 is here, just below, so 3.5 is probably right at the median, so that looks like it's about 50%. Okay, you randomly select one student from the sample. What is the likelihood that the student studied less than 2 hours per day? So let's look at the box plot again. Less than 2. So I would guess 2 is around here, so I'm going to estimate, all I can do is estimate 25%. Okay, use the box and whisker plot to identify the 5-number summary. So the minimum lives at 906. Q1 is at 1,284. Q2, the median is at 1,496. Q3 is at 1998. And the max is 2119. Okay, so here I have the distribution. Okay, so in this distribution here, it looks like it's roughly symmetric. I mean, it's not perfectly symmetric, but there's no reason for me to suspect that it's extremely skewed to the left or skewed to the right. Obviously, it bends a little bit to the right here, but not, in my opinion, terribly skewed to the right. If I were going to say it's skewed in one direction or the other, I would say it's skewed to the right, but for me, it's symmetric enough. Oh, and we got that one wrong. So let's see. If I were looking at this, like I said, obviously it's a little bit skewed to the right, but not terribly. So if we see one like that, I guess they want it to be perfectly symmetric. To me, that's roughly symmetric, not terribly skewed to the right. But if you can see that you do have a little bit of a tail to the right there. box and whiskers. Looks like that's grayed out, so I must have already done that one. So let's try probability. Okay, the probability event that an event will happen is 0.44. Find the probability it will not. So what we do with this is just subtract from 1. So we take 0.44, subtract from 1, and that's 0.56. Hopefully you'll be able to roll right through the probability questions. Okay, so here we have a probability of an event is 23 out of 24. What's the probability that the event will happen? That's probability it won't happen. So the probability that it will, if we want to write that as a fraction, would be 1 out of 24. Find the probability that the event will not happen. So here's the probability that it will happen, the probability that it will not. If it happens 28 out of 41 times, then there are going to be 13 out of 41 left where it's not happening. Oops, did not mean to submit. Just want to move forward. Okay, the probability that an event will not happen is 0.55. Find the probability that it will, so we just subtract from 1. It's all complementary events. Hopefully this is an easy exam question for you. Okay, back to the study plan. And we want the exam. Okay, a realtor uses a lockbox to store the keys to a house that is for sale. The access code for the lockbox consists of 5 digits. First digit cannot be an 8, and the last digit must be odd. How many different codes are available? So let's think about this. So it consists of 5 digits. Okay, if the first digit cannot be an 8, then that means we only have 9 numbers that digit could be. So I start with 9. We use our multiplication rule here. Okay. First digit cannot be an 8, and the last digit must be odd. So that means there's only 5 numbers available for the last digit. And there's 5 digits total. Okay, so I have the first digit, or I have 9 possibilities. And then the next 3, which would be 10 to the 3rd power. Okay, 10 times 10 times 10. There's 10 numbers available for that. And for the last one, it has to be odd, so there's only 5 numbers available for that. So we just multiply how many numbers are available for each spot. 45,000. And we can submit. Wait a second. Here we go. Assume that no questions are left unanswered. How many ways can a 5-question true-false quiz be answered? So, 5 questions. Each question has 2 possible answers. So that's just 2 to the 5th power. 2 times 2 times 2 times 2. 32. Okay. Restaurant offers a $12 dinner special that has 6 choices for appetizer, 11 for entree, 3 for dessert. So 6 times 11 times 3. $198. And now I can submit. 3 for 3. Once we get through probability, we're going to be in much more familiar territory, more things that we have done recently. 5 questions here. And this is a lot. I mean, just if you're feeling like there's a lot of questions on here, this is the quiz me here is kind of overdoing it. The final exam only has 25 questions on it, so there's nothing. I try to make them as easy as possible. So if you can answer these and you're okay conceptually with these quiz me's, you're going to have no problem with the final. A probability experiment consists of rolling a fair 6-sided die. Find the probability event below. I'm rolling a 6. Well, there's only one 6 that I can roll out of the 6 sides. So that's 1/6. Okay. Use the frequency distribution at the right. Find the probability that a voter chosen at random is in the given age range. Not between 18 and 20. Okay. Not between 18 and 20, so it's everything except this 8.7. So the first thing I'd want to do is add everything up. Get this total of everybody that's there. So we add that up. So when I add them all up, I get a total of 150.4. So I'm going to take 8.7, and I'm going to divide by 150.4. Well, that's the probability that somebody's in that age range. Okay, 8.7 divided by 150.4. So I want to take that and subtract it from 1. So 1 minus 0.0578. Let's go 457. And we'll see how many decimal places they want. So I get 0.942. 3 decimal places. So I could add all these up and divide by the total, or I just took the 8.7 since I remembered it, divide that by the total, and since it says not between that, we subtract from 1. Okay. Okay, so a probability experiment consists of rolling a 6-sided die and spinning the spinner at the right. Spinner is equally likely to land on each color. Use a tree diagram to find the probability of the given event, then tell whether the event can be considered unusual. Rolling a number not less than 4. So a number that's not less than 4 will be 4, 5, or 6. That's 1/2. Okay? And then landing on green. Well, we have a 0.25 chance of landing on green. So that's 1/2, which is 0.5. And we multiply that by 0.25. If this is less than 5%, we consider unusual. 0.125 is not really unusual, so yeah, no, because the probability was 0.125, and that was greater than 0.05, so it's not unusual. The probability that a voter chosen at random is in the 18 to 20 range. They probably gave me different numbers now, didn't they? So we have to add all these up again. Let's see what's on this table here. Not going to be super helpful. So we got to add them all up again. It's a good thing I added them up there. They add up to a different sum. It's 140.2 this time. But this time they're asking me the probability that somebody is in that range. So that's going to be just 4.4. It's less work here. 4.4. And then we just simply divide by 140.2. So 0.031 to 3 decimal places. Oops. So here we want to be careful. We have 25, 50, and 25. So it actually geometrically does look the way it is. So the probability that a bulb chosen at random is red, 25 out of 100, right? There's 100 total, so that would be 0.25 or 1/4. Uh-oh. What did we do wrong in question 1? Oh, okay. I think I put a fraction here. Yeah, so 1/6 and 0.167. I did not follow directions. Yeah, type an integer or decimal to 3 decimal places, so they didn't want my fraction there. But 1/6 is correct. But watch that, especially on the exam. You do have a couple of attempts on the exam, I believe. So if something went sideways like that on you, I think you can have a do-over on that. Okay. Okay, so grayed out sections here. Probability distributions. I don't recall putting a lot of these on here. At least not binomial ones, but the expected value of probability distribution random variable, always one of possible x values of x. No, that's not true. It's just an average, right? So the expected value may not always be a value of x, but it represents a large number of trials. So like if I roll a single 6-sided die many, many times, what's my expected value? Well, it's the average of the numbers 1 through 6. It's 3.5. Well, I can't ever actually roll a 3.5. That's okay. Okay, True or false? Expected value of random variable can never be negative. That is false. We go to the casinos and play the games there. There's certainly negative expected outcomes. That's why the casinos can stay in business. What is the significance of the mean of a probability distribution? It's the expected value of a discrete random variable. This is not always the most likely. It might be, but it's the expected value, right? And by that we mean we're not expecting it to happen necessarily, like a 3.5 when we roll a die. It's just what happens in the long run. Okay. So discrete probability distribution, remember the variables take on countable numbers, right? So it has to be a number like 1, 2, 3, 4, so on. Okay. Continuous distribution takes on decimal value. So when we consider that, like if we had the numbers 1 through 6, accompanying them we'd have 1, 6, 1, 6, 1, 6, all of their probabilities. Two conditions that determine a probability distribution. Okay. So not a big mystery here. The probabilities for each value can be any number between 0 and 1, but all the probabilities, all the events, must add up to 1 for it to be valid. Okay. And what is a random variable? So when the variable takes on a number value, those are our random variables. We're not talking about categorical labels here. Okay. Back to the study plan. Okay, discrete or continuous. So remember, discrete means that it takes on a countable number, like 1, 2, 3, 4, 5, or 6. Continuous means it can take on decimal values. Okay, so volume of blood, that's going to be continuous because it could be decimal values for the volume of the blood. Discrete or continuous, number of motorcycle accidents, that's going to have to be discrete because it has to be, you can't have 103.7 accidents. The temperature of a person, that's going to be continuous. They could have a temperature of 101.3. All right. X is the number of light bulbs that burn out. This is a discrete random variable because it takes on a countable number of possible outcomes, for sure. Okay. Does this graph represent a discrete or continuous random variable? Choose the correct answer. Home attendance of football games at a university, it's going to be discrete. Because the attendance is a random variable that's countable, right? We take on countable number values for that. So the normal distribution leads us into, hopefully we can do these calculations pretty easily with our calculator. Here we have a mean of 80 and a standard deviation of 5. If you remember, this is less than 77, so we want to use that normal CDF on our calculator. Second vars, we go to normal CDF. Our lower limit can be negative infinity or 0 or just negative 1,000. Okay, and then we think about our upper limit is going to be 77. The mean is 80. And standard deviation is 5. So try to picture what this is. Recall what we're talking about when we're dealing with these normal distributions calculations. $80 is the mean, it lives in the middle. They're saying 77, we want the probability it's less than that. So my lower limit just somewhere out here, negative infinity, negative 1,000, anything you want. Upper limit 77, the mean is 80, and the standard deviation was 5. They gave us that. So I get 0.274. 4 decimal places. Great. That's the 4th decimal place. 0.2742, which is going to get rounded up to 3. There's a 5 after it. Okay, 75 to 78. Mean is 88 now. Standard deviation is 5. So we have our lower and upper limit now. The lower and upper limit are 75 and 78 explicitly. This time I believe the mean is 88. And I get 0.018. I'm going to assume they want 4 decimal places again. 0.0181. Okay. Greater than 42. Mean of 50. Standard deviation of 7. So try to picture this. Okay, so now the mean is 50, and we want greater than 42. So 50 lives in the middle here. 42 is over here. So 42 is our lower limit, and then our upper limit just needs to be something really big, like 1,000 or 1,000,000, something really large all the way out there. Okay. Okay, so 42 and then something really large is my upper limit. So we want normal CDF. .42 is the lower limit. Let's take something really high as the upper limit. Can't go too high here. It goes off to infinity basically. The mean is 50. Standard deviation is 7. .8735. Looks like we're ready to submit. Okay, great. So that's our normal CDF stuff. Not too bad. Probabilities. Okay, so now they give us a picture, but we're doing the same thing, right? My lower limit's 200, upper limit's 350, and then here's my mean and my standard deviation. Mean is 511. Standard deviation 122. .0881. So this one has several layers to it. In a survey of a group of men, the heights in the 20 to 29 age group were normally distributed, with a mean of 68.6 inches and a standard deviation of 3 inches. A study participant is randomly selected. Complete parts A through D. Probability that the study participant selected at random is less than 67 inches tall. So that's going to be normal CDF. We'll go 0 to 67. So lower limit 0. Upper limit 67. The mean is 68.6. And standard deviation is 3. .2969. Okay. Probability that they're between 67 and 72. So they give us our lower and upper limits again. 67 to 72. And we haven't changed the mean or the standard deviation, so I'm going to leave them alone. Still the same. 0.5746. Okay. More than 72. Let's go back to the same thing. So now 72 becomes my lower limit. More than 72. So let's just put something really high here, like 1,000. Can't go too high with that. 0.1285. Identify any unusual events. Well, we don't have anything that happened less than 5% of the time, so there are no unusual events here. Nobody unusually short or tall. Okay. Same idea here. Probability of scoring less than 17. Mean is 21. Standard deviation is 5.7. So when we go less than 17, because that standard deviation is 5.7, let's go to like negative 100 here. Go really, really low so we don't miss any probabilities. And we want it to be less than 17, so 17 is our upper limit. The mean is 21.1. And standard deviation is 5.7. So 0.23. So if we go to 4 decimal places, that's going to have to be 0.236 because the 9 has to go up. Between 16.1 and 26.1. Mean and standard deviation stay the same. 0.6196. And then more than 32.6. So more than 32.6. 32.6 becomes my lower limit. Can't find it here. And then for my upper limit, we just make it something really high. 100,000. 0.0218. So we did get an unusual event there, 0.0218. Event in part C is unusual because it happens less than 5% of the time. Nothing else is unusual there. Okay, use the normal distribution at the right to answer the questions. What percent of scores are less than 19? So that's going to be a normal CDF. Okay. Second vars, less than 19. So again, let's start somewhere at like negative 100. 19 then becomes our upper limit. The mean is 20.2. And standard deviation is 5.3. .4104. So 41%. I think that would be a 0.4104 is 41.04%. About blank scores would be expected to be greater than 21, so we've got to do normal CDF again. Greater than 21, so we've got 21 here. Let's go to 1,000, let's go somewhere high. Mean and standard deviation don't change. 0.4400. Oh, so that's 44% out of 1,500. Tricky. Notice it said how many, not what percentage. So 660 roughly. take that percentage out of the total. Last one. The amounts of time per workout an athlete uses a stair climber are normally distributed with a mean of 23 minutes and a standard deviation of 6. Find the probability that a randomly selected athlete uses a stair climber less than 20 minutes. So let's go all the way to like negative 100. And the first question here is, what's the probability they use it less than 20? What's the mean is 23 and standard deviation is 6, right? Okay. So I get 0.30. Let's see how many decimal places they want. 4. 0.3085. Between 23 and 32. So the lower limit is 23. Upper limit is 32. Still the same mean standard deviation. 0.4332. And the last one, more than 30. So now 30 becomes my lower limit. Upper limit, something really big, like 100. Nobody's going on the stair climber for 100 minutes. 0.1217. Hopefully I didn't make any errors there. So far, so good. Okay, so we're finally into a little bit more familiar territory from test 3. So here we are the rest of the way here, and this exam review will be all things that we just took on our very recent test. Let's see, I don't know if I can get into the quiz me here. It's not letting me in there. Let's see if I can double back to it later. But confidence intervals for means, we use the t-distribution. And so this gives us the margin of error and the estimate anyway. It's the same concepts that we missed in that grayed out button. So use this interval to find the margin of error and the sample proportion. So the margin of error is how much we add and subtract to get the interval. And the p-hat, the sample estimate, lives right in the middle. So I'm going to do the same thing almost with these two numbers. I'm going to add them together and divide by 2, and I'm going to subtract them and divide by 2, and that's how I get my two numbers. So for the first part, to find the margin of error, that's basically the width of the interval, how much I add and subtract each way. If I take 0.631, let's take 0.661, the bigger one first. 0.661 minus 0.631. That's basically the width of the interval, but I got to divide that by 2 because the margin of error is what you add and subtract from the middle of the interval to get it. Now, if you use the trick on the calculator I showed you, second enter, and just float back over to this minus sign, make it a plus sign. So now we get our margin of error and our point estimate. So basically we took 0.646 and we added and subtracted 0.015, and that's how we got that interval. So the margin of error is 0.015, and the sample proportion, p-hat, that lives right in the middle of it, is 0.646. Okay. Same thing again. Add and subtract them. Just give you a lot of practice with these. So I go 0.797 plus 0.773 divide that by 2. And then use my trick to make your, oops, and then use the trick, second enter, and we can just go back and subtract them. Okay, so I did it in the opposite order that time, but margin of error is 0.012. And then p hat, the sample proportion that lives right in the middle of that, is 0.785. And that is it. Done. Back to the next one. So that same button that was grayed out, that's all that was. I don't know why it was grayed out yet. Calculate margin of errors. You know, that's same thing. So they let me do it. Confidence intervals for proportions. Okay. So why is it necessary for those two numbers to be greater than 5? It's so that we know that we have a normal sampling distribution. So I'm looking for one here that's going to may not be normally distributed, thus we can't use it to calculate the interval. So I want to make sure that I have a normal distribution. That's the purpose of that check. Is this true or false? The point estimate for the population proportion of failures is 1 minus p hat. That is true. Right? P hat is the estimate of successes. 1 minus p hat would be failures. To estimate the value of p, we take successes out of the total. So it's this one here, x over n. Right, total. Oops. Use point estimate x. Yeah, so that's false. We use point estimate x over n. They did say true. So it's a proportion. It's a decimal, right? So we have to take successes out of total trials. Okay. Confidence interval for proportions still. So in a survey of 2,065 adults in a recent year, 1,301 say they have made a New Year's resolution. Construct 90%, 95% confidence intervals. Okay? So these are the two values I need. I go right to the calculator. 1,301, 2065. This is under stat, test, and this is a 1 proportion z interval. So you might have to go down a little ways to find it. 1 prop z interval. We're doing confidence intervals first. So they gave me the number of successes was 1,301 and 2065. And we'll do 90% first. And I think everything will still be in here when we double back to do 95%. So for my 90% confidence interval, they want 3 decimal places. So 0.613. Up to 0.648. And then for 95, do it again. Stat, test, and then just get down to your 1 proportion z interval. .609. to 0.651. Okay. Was the given confidence? It can be said that the population proportion of adults who say they made a New Year's resolution is between the endpoints. Okay. Compare the widths. Well, remember, 95 is always going to be wider than 90, right? You're going to have more confidence, so 95% has to be wider. Okay. So figure to the right shows the results of a survey in which 1,020 adults from country A, 1,025 from B, and so on, Ask whether national identity is strongly tied to birthplace. So 95% confidence interval for folks from country A. So we have to do a bunch of intervals given these percentages. So for country A, the point estimate was 31% out of 1,020. Okay, so we go stat test, 1 proportion z test. I'm sorry, 1 proportion z interval. Test menu. Tests are next section. So again, remember it was 31% out of 1,020. So 0.31 times 1,020. And we'll have to round that to the nearest whole number. Yeah. So the calculator is not going to accept this. It's going to go crazy. It has to be a whole number. You can't have 316.2 people that agree with that. So that would be 316. And let me just double check my confidence level. I'm doing here every time. 95 every time, right? Okay. So 0.2814. All the way up to 0.3382. Next one, country B, where you had 20% of 1,025. So here I have a 20% of 1,025. And that happens to be a whole number. So I don't have to correct that. And we get our interval. Okay. So 0.1755 up to 0.2245. Okay. Country C, 23% of 1,009. So 0.23 times 1,009 out of 1,009, and we'll have to go back and correct that. So that should be 232. It's still 95. So I get 0.203. The 9's going to go up, so it's going to be 0.204. Up to 0.2559. And now we got country D. 46% of 1,005. So that would actually be 462. And still 95%. 0.4289. Up to 0.4905. And one more time. 13% of 1,005. Okay, so that's going to have to be rounded up to 131 for that to work. So 0.1095 up to 0.1512. Okay. So now we have 1478. We want a 99% confidence interval. 1478 out of 2761. It was 2761. Just let me double check my numbers there. 14782761. Yep. And we want 99% confidence. Remember. So 0.5109. And I just read that the last second. It's 3 decimal places, so that'll be 0.511. And 0.55. So the 9's going to go up, so that would just be 0.56. 0.560. With 99% confidence, it can be said that the sample proportion, sample proportion we know is in there, 100%. We're 99% confident that the population proportion was in there, the parameter of interest. That's what we want there. Okay, so I'm going to move on from the proportions to confidence intervals for standard deviation. This is our chi-square distribution. So we want to recall how we look up some critical values for the chi-square distribution. Hopefully they give us a chi-square distribution that we can look at. If not, we need to pull up the e-text. Okay. So find the critical chi-squared right, chi-squared left for the given confidence level. So I'm going to need my e-text open here. So I grab the chi-squared table for my e-text, and we go and we look. Our sample size is 17, so we're going to have 16 degrees freedom, and we want 80% confidence. So 16 degrees freedom, 80% confidence. So 16 degrees freedom is down here. 80% confidence means that we're going to have, I don't know if I can write on here or not, but for 80% confidence, I just want to look at these two columns right here and here, 90 and 10, right? Because there's 10, if there's 80% in the interval, there's 10% in each tail. So I go through 16. My chi-squared left is going to be that 9.312. And then chi-squared right, be right next to it, 23.542. Okay. Same deal with this one, chi-squared left, chi-squared right. So I'm going to move on. So the next part of the study plan, we want to calculate the confidence interval for variance and for standard deviation. And if you remember, we're going to lean on StatCrunch for this. Okay, so I don't have actual data. I have the confidence level. Standard deviation is 36. So let's be careful of what StatCrunch is going to ask us for. So if I go to Stat and Variance Statistics, this is one sample, and it's with summary statistics, not with the data. Okay? So I don't have the sample variance. I have the sample standard deviation. So I have to take that 36 that they're giving me and square it. So the sample variance is 1296. The sample size, they gave me that outright, was 36. And hypothesis test is for the next chapter. We'll do the confidence interval and just check what level they wanted. 98. Okay, so I have the confidence interval for variance here, 791. the first one they asked for, 2 decimal places, 7. So 791.04. Up to 2450.71. Confidence interval for population standard deviation. We just take the square roots of those two numbers. So the square root of 791.04 28.13 and square root of 2450.71. So just 49.5. So John, I'm not sure if you're using Google Chrome. If you are, if you see these 3 little dots up here, left click on that, and then you go down to Settings. And then in your settings, it should look something like this. And under Clear Browsing Data, you can come in here and clear everything. Right? So if I hit Clear